Okay, so far we have covered what a stochastic UE is, why do we need a stochastic UE, because of the imperfection knowledge of the travel times across the network. People don't really have a exact knowledge of what the travel times are, and we went over the route choice modeling using the utility maximization theory, where we define a utility function and then we try to calculate the probability of each path being selected using the logit formula given that utility function. And now we're going to move into formulation of the stochastic UE. So similar to all the other UE formulations with fixed and elastic demand that we've covered so far, we can actually formulate a stochastic UE. The deterministic UE, in the deterministic UE, we assume that users take the shortest path between each OD pair, right? But in a stochastic UE, in fact, that's no longer true because everything is based on perception of travel time. So the selected paths may not necessarily have equal actual travel time. In a stochastic UE, we say that the total travel demand for an OD pair is actually a split according to the proportions that we calculate based on the logit probabilities. So whatever probability I calculate for my possible route, 70%, 60%, 20%, the path flows will come from those proportions, regardless of the whether the route travel times are going to be equal or which one is greater than the other one, except that the travel time calculations and the travel time comparisons are implicitly taken into account in the utility function and the logit formula. If the utility function, assuming the utility function carries that travel time variable in it, right? But then there's a problem here that we need to know how many possible passes exist between one origin to another destination. And do we want to split the demand into all of these paths or just maybe a couple of them or a set of them? So then this question rises up that says, can we enumerate all the existing routes in the network and determine their associated proportions? In theory, the answer is yes. Yes, obviously we can get all the possible passes between R and S and then try to come up with the proportions for them. But in practice, it's very difficult. It's very computationally expensive. So for example, if a network has n nodes, then that means we have n factorial paths in it. And that is just too many. And we can't really, so imagine just imagine this very simple network. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes. And look, there are many, many passes between every OD pair here. So if you want to go from, let's say from R to S, let's see how many passes exist. Why do we care about how many passes exist between R and S? It's because that will be the set of that would be my alternative set. That would be my choice set where I want to pick, where I want to select from. That means how many alternatives do I have when I want to select, when I want to find out when I want to find out the path flows between R and S. So I have this path, I have this path, I can go this way, I can go this way, I can go this way, I can come this way. There's so many things, right? There's so many possible passes that you can go from R and S, and it's just too many to take all of them into account. So that's where the stochastic network loading problem comes in. That says, that aims to determine the user's choice set. So if this is my origin and this is my destination, then these are all the possible passes going between them. How about instead of just going after all of them and considering all of them in my choice set to calculate the probability, how about I just go with a set of most used paths? I can just, for example, select this one and this one and this one that are more reasonably are more likely to get selected. And I can just ignore the other routes because maybe they're just too long, or their travel time is just too high, or maybe it's just unreasonable. Nobody will select that intuitively. So one way is actually manually select a set of most used paths. The other approach, which is probably a bit more systematic, is we call it a K shortest path algorithm. Apply a K shortest path algorithm, meaning that how about I find the 5, in this case, it would be 3 shortest path in this example that I said. How about I find 3 shortest paths? So I try to find the best shortest path, the second best shortest path, and the third best shortest path. And then I would say, I'm going to limit my path choice. I'm going to limit my choice set between each OD to only 3 possible passes. So I don't need to calculate all those probabilities for all the possible passes. So that would be called the K shortest path algorithm. And there's another method called Dial's method, which tries to define an acyclic subnetwork that only contains efficient links such that the travel time of that link I is smaller than the travel time of link J. I'm not going to talk much about the Dial's method here, but again, just wanted to tell you that there are many different ways of determining that user's choice set when it comes to a stochastic network loading. And then once a choice set is known, whether it's manually selected or just totally arbitrarily or using a K shortest path algorithm, then we can calculate the probability of each route being selected using the logit formula and the given utility function. But let's go back to the formulation of a stochastic UE. So we knew that the travel times on links are dependent on flow, right? If the flow goes high, travel time goes high. If the flow goes down, travel time goes down. Interestingly, when it comes to mathematically formulating SUE, we actually end up with an on-constraint optimization problem. Remember, the actual UE, we had a couple of constraints, right? We had the non-negativity constraints, we had the flow conservation, we had the demand conservation. So we had a couple of constraints. But interestingly, when it comes to formulating SUE, this can be formulated as a totally on-constraint optimization. We try to minimize the objective function of SUE, which is formulated as this. So this is my new SUE optimization formulation, which says, what is the first term? Summation of the volumes multiplied by the travel times. That is actually TSTT, right? Total system travel time. Minus summation of the integral of TA. This is actually my Beckman function, or my UE objective function, right? And what was this TSTT? This was representing SO, system optimal. So the first term is actually the system optimal objective function minus the UE optimal objective function and UE objective function. And then this is the last term that takes into account the stochastic nature of the SUE problem, where we say summation across all the ODs, we multiply demand by this SRS. What is SRS pi? SRS actually represents the expectation of the minimum perceived travel time. And again, the reason we call that an expectation of the minimum perceived travel time is because everything is probabilistic here, right? So whatever that expected value is, expected value of the minimum perceived travel time comes here, and then it gets multiplied by the demand. And then if you sum it up across all the So this is also in term. This would be in terms of this. The unit of this term would be travel time, right? This would be time, and then it gets multiplied by the demand, just like TSDT. It's time multiplied by flows. And this SUE program is unconstrained because, interestingly, as I said before, if we find out the solution of this problem, we can see that it already satisfies non-negativity and it already satisfies the link and path flow equations that we had before. So when it comes to unconstrained optimization problems, how can we find the optimal solution? Do we need what would be the do we need optimality conditions or anything like that? Do we need Lagrangian function? No. If we have an unconstrained problem, we just need to simply take the derivative of this. So we just need to simply take the derivative of this function z with respect to x, make it equal to 0, and find all the link volumes that we want. So I think I talked about this. The first term in the SUE formula is SO. The second term represents the UE objective function, and the last term is representing that expected value of the, so this would be the expected value of the minimum perceived travel time. And as I said, no Lagrangian function is needed. We can just simply take the derivative of that ZSUE and make it equal to 0. And interestingly, if we actually write down the optimality conditions of the SUE, we can actually find out that the derivative of this S function, the expected value with respect to the path cost, is equal to that proportion that we talked a lot about before. But anyways, just a little bit on the formulation. Let me see if I'm, yes, now, good. Now we're getting into an example, finally, right? So now that we know this is how the SUE problem looks like, how can we actually solve this optimization? So the approach that we're going to take is going to be similar to the previous problems that we had with UE with fixed demand or UE with elastic demand. But this time, we can use actually a descent algorithm to find the descent direction and determine the optimal move size at every iteration. Very similar to MSA, right? So what we do is we solve the stochastic network loading problem. What does that mean? That means we find the possible paths we come up with the choice set, basically. We come up with a choice set. If between each OD I have many, many possible passes, I need to come up with a choice set. I could either say, I want to consider all the possible paths, or I could say, I want to go with the three shortest, I want to apply a K shortest path algorithm, and K could be equal to 3, 4, 5, whatever. And then now that I know what is my possible paths between each OD pair, I assign the travel proportions to the selected routes using the logit formula, the logit model that we covered earlier. And as I said, we're not going to talk about probit model in this class. Now that we calculate proportions and we assign the demand to different passes based on the proportions, I can find the optimal or the steepest descent direction. And then I can determine the optimal move size using MSA, for example, which uses a fixed step, basically. Frank-Wolf is not appropriate here because the objective function that we deal with, this objective function is just too complex for Frank-Wolf algorithm. Remember, in the Frank-Wolf algorithm, if you want to calculate that lambda value, we have to take the derivative of this, and at every iteration with respect to link volumes, etc. And this is just too complicated for Frank-Wolf. So usually we don't do Frank-Wolf algorithm when it comes to SUE and the common way of doing it is just with MSA. And there are other methods as well, which we're not covering in this class. And then we continue this, again, just like any other iterative method that we covered before, until we reach convergence, however we define convergence, whether it's the gap, relative gap, or whether it's reaching a specific error threshold, etc. So let's have a look at an example. So the first one that we're going to talk about is we're going to solve this algebraically, actually. So very similar to all the previous examples that we had in the class. We have a very simple network from R to S, only one OD, two links. Link travel times functions are given. I have my demand, and I want to write down the simultaneous equations. I want to write down the system of equations that I can use to actually solve this SUE problem algebraically. So let's just start with the utility function. So in this problem, I am giving you the utility function. So the utility function is actually gonna be just, remember the generic equation of it was minus theta t, right? So in this case, I'm giving you the theta value. So it's gonna be u minus t. So u1 would be, and ut would be this one. So these are my utility functions that is given. And we just now need to write down the simultaneous equation. So how can we do that? What kind of equations can we write? We can, of course, we can write something about the demand conservation, right? Because again, if this is my x1 and this is my x2, definitely x1 plus x2 must be equal to the demand, and demand is 4. So x1 plus x2 should be equal to 4, just making sure all the demand is loaded into the network. And I can also write down two other equations. But where do I get this? So remember I said before that the flow of a path is equal to the proportion of that path multiplied by the demand, right? We had this equation. So that means flow of path 1, which is in this case would be equal to x1, is equal to the proportion of people who are taking path 1 multiplied by the demand, which is 4. So x1 is actually p1 multiplied by 4. Same thing applies with the second route, right? So f2 is also equal to x2. It's only a path with one link, so f2 is actually equal to x2, is equal to p2 multiplied by the demand, which is 4. So x2 is actually equal to p2 multiplied. So I now have three equations. I have x1 plus x2 equal to 4. I have x1 equal to p1 multiplied by 4, and I have x2 equal to p2 multiplied by 4. And I can actually replace this p1 with the logit formula, right? Because this p is coming from those probabilities, like it is equal to the probabilities, right? So p1, what would p1 look like in a logit form? So the probability of route 1 being selected is actually equal to exponential of route 1 over summation of exponential of route 1 plus exponential of route 2. Okay? And now if I just simply replace the utility functions into this formula, I would get, sorry, let me erase this. I'm not sure why I can't erase these things anymore easily. Yeah, it's erased. So that would be exponential of minus t1, exponential of minus t1 plus exponential of minus t2. And that is equal to what? x1 over 4, right? Because we're dealing with this. So we're saying this says p1 is equal to x1 over 4, right? So we're just replacing p with the logit formula that we had. So I can do that for p1. That's what I did here. And I can also do it for p2, easy. The denominator will remain the same. Only on the top, I need to replace this e exponential of minus t1 with exponential of minus t2. And again, remember, this is not t1 multiply x1, okay? It is not t1 multiply x1. No, this is t1 as a function of x. So again, in the past, some students have made the mistake that they thought this is t multiply x. No, this is t as a function of x. So it's just t. So I now have three equations, right? So if I come down here and then if I actually try to simplify this equation that I wrote down in the previous slide, I can actually simplify it. And if I try to solve it, and I had this x1 plus x2 equal to 4, so that means x2 is actually 4 minus x1. So I had three equations, two unknowns basically, and I can easily solve it, right? So I put this into the equation, I solve this, and if you actually continue till the end, I leave this to you to do the calculation. It's an easy calculation. You end up with x1 equal to 1.75. And if you also calculate x2, which is simply just 4 minus x1, you end up with 2.25. So these are my link volumes. And let's also calculate T1 and T2, because that would be very interesting to see. So these are my SUE solutions, okay? So this is my SUE solution. But let's have a look at the travel times, because it is very interesting. What would be T1? Again, if you put this into the travel time function of link 1, so this is the travel time function of link 1, and this is the travel time function of T2. So if you put these numbers into that, T1 would come out as 4.5 and T2 comes out as 4.25. Interesting. Look, T1 is not equal to T2 because we're not solving UE, we are solving SUE. If it was the UE problem, we must have had T1 equal to T2. But when it comes to a stochastic user equilibrium, no, T1 could be different than T2 because everything is based on perception of the travel time. The actual travel times could be different. And in this case, the actual travel times are 4.5 and 4.25. And the link volumes are this. So this was an example of how we can algebraically solve SUE. So the next example, we're going to apply MSA, but with a little bit of some modification to account for that stochasticity. So here's a more complicated network, not super complicated, obviously, but a bit more complicated than the previous example. So algebraic solutions may not necessarily work here because I have 5 unknowns and it would be too difficult to, again, not super too difficult, but it would be more difficult to solve this by setting up this system of equations and trying to come up with that algebraically. That's why we apply the iterative heuristic methods. So we have this origin destination, demand is 20. I have 3 possible routes, right? This route, and this route. And let's apply, and also let's assume the utility function is as before. So it would be just u is minus t, or basically u theta t with theta being equal minus 1. So the utility function is minus t as before. And we're going to find, the problem is asking us, find the SUE link flows. Okay? And we're going to apply MSA. Let me actually do this in Excel if you're all happy. Let me go after one, let me show you one iteration in the slides, and then I'll continue with that in Excel, just like what we did last week. So how should we start MSA? We assume we start with the empty network, right? So we assume nobody's in the network. Network is empty. So let's find the link travel times. So we have the link numbers. Network is empty. So this is empty network. So this is applying MSA. And we get the link travel times, right? So these are my X0s and T0s. And then from that, from this x zeros and t zeros that I have, I can calculate the path cost, right? So I had this path, I had this path, and I had this path. So I have three passes. ABD is in the bottom. So this is ABD. The middle one is ABCD, and the top one is ACD. So ABD would be 20 because it's actually T1 plus T2. ABCD would be T1 plus T3 plus T5, so that would be 10. And ACD, which is on top, would be T4 plus T5, which is 30. And now remember, if it was the original MSA and the UE, the traditional UE, or deterministic UE, let's call it, what should we do now? What should we do next? We would do an all or nothing assignment, right? It's the time to do all or nothing assignment and load all the demand to this shortest path ABCD. But we don't do that anymore because we know that in a stochastic UE, people will be split to all these possible passes between this origin and destination based on some probabilities that we have to calculate given the utility functions. So now for every path, we calculate that PRSK. And PRSK comes from the utility function, comes from the logit formula, which says utility of K over summation of E utility of L. So in this case, P1 would be exponential of U1 over exponential of U1 plus exponential of U2 plus exponential of U3. Okay? So I will use the logit formula, and I have the utility function. Utility function was a minus t for every link. So if I calculate this, I'm going to calculate this in Excel in a minute. If I calculate all of this U values, so I can calculate U1, U2, and U3 for every path, and as a result, I can calculate P1, P2, and P3. And then how do I convert P to F? We said FRSK is actually PRSK multiplied by the demand. So I just need to simply multiply these P values with the demand. Demand was 20. So I just multiply these probabilities by 20 and I get flows. And again, you can check the summation of this flow. The sum of these flows must be equal to the demand, which is 20, right? So just checking if everything is correct. So now that instead of all or nothing assignment, I do this SUE here. I apply this logit formula here to get the probabilistic path flows. And from these path flows, I get my link flows. So if I know the path flows, I can easily get the link flows, right? And again, here, this could be X star, sorry, just to be consistent with previously, but then X star previously was all or nothing, but this time is a result of application of a logit model, not all or nothing assignment, okay? So we don't do all or nothing assignments here. We apply the logit model to get the X stars. So we get the X stars, we put it in the MSA formula, and we get X1s. This is iteration number 1. Obviously, lambda value is actually equal to 1. So again, X star would be equal to X1. But in iteration 2, lambda value would be 1 over 2. So we can calculate X2, X3, and so on and so forth. Okay? I have the rest here, but I want to do it in Excel if you all agree. This was the network. So we're going to apply MSA. So this would be using MSA to solve for SUE. Okay. So let's start with links. So I have link 1, 2, 3, 4, 5. I have the travel time. Sorry, let's do X and T. So let's go with X0 and T0 for now. Now let's do it this way. So x0, let's start with an empty network. And is there any question? I sometimes hear a beep. No. So T0, what is the travel time of link 1? It's actually 2 multiplied by x1. Travel time of link 2 is 20 plus x2. Travel time of link 3 is 10 plus x3. Travel time of link 4 is 30 plus x4. And travel time of link 5 is actually equal to 5. So that is my links. And then I have a set of paths, right? So let's also write down the paths. So I had, let's just to be consistent with the slides, I had ABD on top. So it's ABD, ABCD, and then ACD. And then I can also get its travel time. So that would be path travel time. In this case, what would be the path? What would be the travel time of path ABD? It's actually T1 plus T2. ABCD would be T1 plus T3 plus T5. And ACD would be T4 plus T5, right? So these are the travel times. And yes, they look correct. And again, I don't care about which one is the shortest path, right? Anymore. What I can do is I need to apply the logit formula now. So to do that, let's write down the utility function. What I can do next to this travel time is I add the utility function here, utility. What was the utility? It was minus 20, minus 10, and then minus 30. Oh, I just remembered, I think the utility function in this example is actually, theta is actually not -1, it's minus 0.1. So let me just clarify it here. So theta is actually 0.1 here. So that means I need to multiply this by 0.1. Yes, and we can check. We can double check whether I'm doing it correctly. So I have the utility values, and then I need to calculate. What I can do is I can also calculate the exponential of the u just to be a little bit more clear. So I calculate the exponential values because I need it in the logit formula, right? So now I need the probability. So let's call them P. What would be the probability of path 1? It would be exponential of this utility divided by this exponential plus this exponential plus this exponential. And let me just double check that with my slide. So the probability is 0.24, and I have the same. No, I don't have the same number in my slides. The probability of in my slide is, oh, sorry, no, that is correct. I got, yeah, it's correct. Yes, it's 2447. Yes, good. And let me calculate this. I just need to make sure I do the formulas correctly. Oops, what am I doing? Okay, let me do this again. So this would be, the probability would be u exponential of this path divided by this exponential plus this exponential plus this exponential, and this one as well. This would be this exponential divided by this exponential plus this exponential plus this exponential. Remember, sometimes the students make a one very common mistake here is some students forget to take the exponential value, and they simply calculate probability using utility. So they would say utility of this path divided by the summation of the utilities. No, that's not right. It's the exponential of the utility divided by the summation of the exponential of the utilities, okay? And then let's double check whether the summation of all the probabilities are equal to 1. So that would give us a reassurance. Yes, so the summation of the probabilities are 1. But look, this is interesting. So far, let me maybe give this a little bit of a color. So we calculate the proportions that we talked about, and then what would be the path flows? F is simply probability multiplied by the demand. What was demand? The demand is 20. Yes, this is correct. So this would be now my path flows as well. Let me also give it another color, slightly different. So this was the proportion. These are the path flows. And again, if you obviously the summation of the path flows should be equal to the demand, right? So this summation should be equal to 20. Yes. Let me keep them just in case we want to double check. So let me just write it down. Here is the demand. This would be the prop sum, let's call it. So it's 1 and this is 20. So now that I have the path flows, I can actually calculate X stars, right? So let me do X star here. I can write X star here. So what would be my X star? So link 1, what is the link 1 volume? It's actually just ABD. The volume of link 2 is actually, again, just coming from the flow of path ABD. Oh, no, sorry. Link 1 is actually ABD plus ABCD. Yes, it's ABD plus ABCD because it's a shared link between two paths, right? Link 2 is it only belongs to ABD. Link 3 also just belongs to one path ABCD. And link 4 is also just ACD. And link 5 actually belongs to two paths, ACD and ABCD. So that means ABCD plus ACD. Yes, so these are going to be my link volumes, X stars, okay? And if I want to apply, let me just get these. Yeah, so X1. Now, what would be my X1 if I want to apply MSA? Let me just put the lambda value here. So if this is my lambda, lambda is 1 here. We are at iteration 1, right? Okay, let me call it iteration. That's better. Let me also put it here. Iteration, it's iteration 1. So it would be, what was the formula? The formula is x0 plus 1 over I. So it's x0 plus 1 over number of iteration, this is MSA formula, by the way, x star minus x0. X star minus, sorry, this should be multiply, x star minus x0, yes. Obviously, it is equal to, like, the reason I'm putting the formula here, because, again, we know in, oops, I think my iteration number should be, let me just fix the number here, yes. And cool, this is good. So I got my x1s. So now it's time to go to the next iteration, right? So let's start with iteration 2. So let me take all of this and copy it here. And let's see if everything is going correctly. So this is going to be iteration 2. I want to change this to x1, and this would be x2 again. Let me see if the travel times x1s needs to be updated. So these are x1s. Yes, good. Let's check. So I have x1s correct. Let me also call this t1. So t1s, they have the right formula. Therefore, we can get the path travel times automatically. utility functions are calculated, exponentials of the utilities are calculated, then I calculate the proportions or the probabilities, and then as a result, I get the path flows and the summation is 20. So that looks all right. Let me just double check with some of the numbers I have in my slides. So I just make sure I don't make any mistake because I'm doing this on the fly. Yep, it looks okay. And I have the path flows. I get the X stars from the path flows. I apply the MSA formula. Let me just double check the MSA formula here. Yes, it is taking the right iteration number on the top. So these are my new link volumes, right? So let's do another iteration. Then it's easy. Yay. Let's do iteration number 3. So I just need to make this equal to 3. Let's update some of these column names. So this is T2, and this is going to be X3. And yes, it's going well, apparently. So let me just do another iteration. And this would be iteration number 4. This is X3, T3, X4. Let me just double check if everything is correct. Yeah, it looks all right. So path flows, yeah, and you can see, look at the link volumes. It's this is still fluctuating, right? So let's do a few other more iterations. So let's do iteration 5. So this would be, sorry, I didn't fix, did I fix this? Yes. So this would be iteration 5. So this is X4, T4, X star, and then X5. So I get X5 values. And yeah, gradually look at the path flows. Path flows are gradually kind of stabilizing a little bit. So that means we're almost getting to the convergence point. We're converging to the equilibrium point, sorry. Let's do another iteration and then we can check at the convergence pattern. This is iteration 6, so let's do X5, T5, and this would be X6. I think everything else, I don't need to change anything. Yep, that is correct. Let's do another iteration as well, okay? This would be iteration 7. This is X6, T6, and then X7. Okay, let's stop here and let's have a look at how maybe either path volumes or link volumes are. Let's look at the link volumes actually. Travel time, I can actually look at travel times as well. Look, very interestingly, if it was UE and if we were at the equilibrium point, we would expect that these travel times to be exactly equal or almost exactly equal, okay? Can I say almost exactly equal? Almost equal. But because this is SUE, we know that the path travel times will not necessarily be equal because everything is based on perception of travel time. So we can't really use this as a measure of travel time convergence. So what we need to do is we can look at the fluctuations of the path flows or link flows, for example. So let's have a look at the fluctuations of link flows. Let me just put link here. It would be 1, 2, 3, 4, 5, and then these would be iteration. These would be iterations. I'd say 1, 2, 3, 4, 5, 6, 7, and let's just put the link volumes that we calculated. So this is this one. Iteration number 2 is this. Iteration number 3 is this one. Iteration number 4. Iteration number 5. and iteration number 6, and link volume of link 1 iteration 7. And now if I do that for all the iterations, yeah. Okay, so let's have a look at how the link volumes are actually changing. What is this? No, let's do this one. Huh. Okay. Just give me a second. I'm going to fix this. Yeah, this isn't. Yeah, the other one is correct. So this is my link volumes. And you can see that iteration 1, from iteration 1 to iteration 2, let me also change, let me call this link 1. Yes. You can see link 1's flow is actually pretty stabilized, right? So let's have a look at link maybe 5 as well. Yeah, same thing with link 5. Link 5 is also stabilizing. Link 2. Same thing with link 2. Link 3. Yep. And link 4. Sorry, that's not link 4, that's link 5. This is link 4. Yes. So look, I have all my links, and I'm looking at how link volumes are changing over iterations. Why do I have more? Yeah, this is it. Okay, sorry. Yep, that's it. So you can see iteration 1, from iteration 1 to iteration 2, there is a bit of fluctuation. From iteration 2 to iteration 3, there's still a bit of changes. But from iteration 3 forward, things are starting stabilizing. So to be honest, one could say, I'm happy with this. I can consider this a convergence, and I can stop here, right? I can also do the same thing with the travel times. Instead of looking at how link volumes are changing, obviously travel time is a function of link volume. So, but I could also look at the link travel times and how to see how link travel times are changing. But again, it would look pretty much similar. You can actually tell from here that you have all these t-values, and you can see t-values are actually less fluctuating as we go forward. But anyways, this is how the convergence pattern looks like in this example. And again, where to stop, when to stop, you can either set a maximum number of iterations that you want to go, or you can come up with your own or our own defined convergence criteria. We could say, I'm going to stop when the average change in the travel time, link travel times, is smaller than whatever percentage. I want to change when the path travel times don't change as much. I can actually do the exact same thing with, let me do this. I want to now look at the path travel times, okay? So path 1, let me call this ABD, and let's actually compare how path travel times are fluctuating. Are they converging? Are they converging? Are they following the same convergence pattern as link volumes or not? Sorry. 1, 2, 3, 4, 5, 6, 7. So path 1, where are you? So ABD, then I have the second iteration is here. Sorry, I'm looking at the flows. I need the travel times. Sorry. So the first travel time is this is basically when the network is empty. Then iteration 2. And 3. 4, 5, iteration 6, and iteration 7. Okay. And let's have a look at the same. Let me just delete some of them, and then I just need 3 of them, right? So that would be one of the paths, and the middle pass, yes. So this would be my path travel times, right? This is my path travel times convergence pattern. Yeah, it follows pretty much the same pattern. You can see that after iteration 3 and 4, things start stabilizing and path travel times are not changing much. And that is an indication of convergence, I would say. And then you can set up a convergence criteria that, hey, if the changes in the path travel times are smaller than whatever percentage, I can stop my algorithm.